Okay, so good afternoon, everyone, and I would like to begin by expressing my gratitude to the organizers for this opportunity to present my research today, and thank you also for this very nice event that I appreciate a lot. So today I'm going to share our findings on collective behaviors that emerge in two component superfluids of light and matter, specifically focusing on the transition from dissipationless flow to the formation of collective excitations, such as dispersive shock waves within these systems. So to set the stage for the exploration of this phenomena, let me briefly present the realm of two-component superfluids. So this system can be realized in various physical platforms, which include ultra-cooled gases, polariton condensates, but also intense laser fields propagating in nonlinear media. These two-component systems are typically characterized by two distinct internal states, whose macroscopic coherence is captured by two complex order parameters, psi plus and psi minus. So they squared moduli give the densities, rho plus and rho minus, of these two components, and the gradients of the phases, the superfluid velocities, V plus and V minus. So this two-component nature significantly enriches the hydrodynamic behavior, giving rise to two distinct excitation modes in this system. So the first mode, the first density mode, involves fluctuations in the total density rho and the center of mass velocity capital V, while the second spin mode consists in fluctuations in the relative density sigma and the relative velocity small v. And numerous investigations have been done in this system, from few to many body physics, partly including the very phenomena I'll be discussing today, that are frictionless motion and the formation of collective excitations. So basically, two concrete experimental realizations have motivated these theoretical studies. The first experimental platform involves a two-component superfluid of light. It is realized using an elliptically polarized laser in a nonlinear medium. It is conducted in the group of Quentin at LKB in Paris. And here the theoretical understanding of the problem benefits from the participation of Nicolas from the same lab. And we have another platform which consists in a Rabi-coupled two-component Bose-Einstein condensate. It is realized in the group of Thomas Bourdelle at Paris-Saclay. And here the theoretical work is done in close collaboration with Thibaut Congy from Northumbria University in the UK and Pat Sprenger from the University of California in Merced. Okay, so let's now move to the experiment at LKB in Paris in the group of Quentin. So the core of the system here involves a laser in blue, which is characterized by two distinct elliptic polarization components, psi plus and psi minus. And these polarizations are injected into a nonlinear medium. So within this medium, the behavior of light is dictated by the nonlinear optical properties of the medium, which are characterized by three key parameters, G, G plus minus, and rho sat. So G describes interactions between photons within the same polarization. G plus minus describes interactions between the two different polarizations, psi plus and psi minus. And rho sat is some intensity threshold above which the optical nonlinearity saturates. And crucially, in this experiment, or let's say this experimental proposal, we have a second polarized and non-diffracting laser beam, here in red, which propagates along the positive z direction. And this beam creates a local modification of the refractive index of the medium, which is described by this function u plus or minus of x and y. So think of it as a sort of optical defect, optical obstacle for the blue beam, with a typical width w in the transverse x and y directions, which basically correspond to the waist of this red beam. So importantly, the dynamics of these two optical fields is ruled by this nonlinear Schrödinger equation, this two-component nonlinear Schrödinger equation. K here acts as some mass parameter and corresponds to the propagation wave number of the blue beam in the medium. You have the effect of the red beam here, and this big term here is the saturable optical nonlinearity of the medium, which describes interactions between photons and the saturation of the optical nonlinearity. Okay. As you can see, this equation bears a striking resemblance to the Gross-Pitayevsky equation of Bose-Bose superfluid mixtures upon interpreting this propagation coordinate z as time. So this whole optical platform effectively realizes what we can call a two-component superfluid of light, which evolves in time as the blue beam propagates along the z-axis. So this superfluid is two-dimensional. It lives in the transverse xy plane, and it interacts with some polarized obstacle here in red. Okay, now assume that this blue beam is slightly tilted away from the positive z direction. So this effectively realizes a flow for the two components of the superfluid along the x-axis. And we assume, for the sake of simplicity, that the two components far away from the defect share exactly the same background density, rho naught over 2, and the same background velocity v naught. So this is the description of the setup. And now the goal is to understand, or let's say to derive the conditions under which such a flow past this polarized obstacle is superfluid, in the sense frictionless, dissipationless. Okay, so to answer this problem, a first and very basic approach is to use linear response theory, which is valid for a weak obstacle potential. A key prediction here is that when the flow velocity v naught exceeds some critical values, the superfluid will start to lose energy by emitting density and spin Bogoliubov waves ahead of the obstacle, a phenomenon which has been observed in Nice in the group of Claire for a one-component superfluid of light, so let's say in the density mode. And the critical speeds at which this energy loss occurs are basically the typical speeds of these Bogoliubov waves that are the density Bogoliubov speed of sound and its spin counterpart Cs. And according to Landau's criterion for superfluidity, if V naught, the incoming flow velocity, is smaller than the minimum of CD and CS, so if the fluid moves slower than the slowest excitation in the fluid, it shouldn't lose energy via Bogoliubov emission. And so let's say the flow becomes a superflow. This is Landau criterion. So we have CD and CS here plotted as a function of the total background density of the superfluid. So the blue curve is CD, the orange curve is CS. And you can see we have an interesting inversion between CS and CD as a function of rho naught, which is a consequence of the saturation of the optical nonlinearity. At low rho naught, spin wave emission limits superfluidity first, while at larger rho naught, it's density waves. That's life. This is the system due to the saturation of the optical nonlinearity. And another key feature, another key signature of superfluidity is in the drag force experienced by the obstacle. So you can define this force in the following way. This is the average value of the gradient of the obstacle potential over the superfluid wave function, psi plus, psi minus. And you can compute this object analytically within linear response theory. So we did it for a simple disc-shaped obstacle potential with radius W and constant amplitudes U plus and U minus. Or if you want, capital U and small u, which are respectively the sum of U plus and U minus and the difference between U plus and U minus. So this is the result. You have here the drag versus the incoming flow velocity V naught. The most important feature here is at low velocity, below the critical speed for superfluid motion, predicted by Landau's criterion for superfluidity, the drag is exactly 0, which is a strong signature of a frictionless superfluid motion. And above the critical speed, you have two peaks which appear, which basically signal the successive openings of the spin and then density excitation channels, or vice versa, depending on the rho-naught regime you consider. Okay. And of course, the drag has the tendency to decrease at high velocities due to the fact that in this regime, the kinetic energy dominates over the obstacle potential. Okay, so linear response theory provides, let's say, a good initial understanding of the behavior of the flow past the obstacle, but it does not tell us how the critical speed for superfluid motion depends on the obstacle properties, such as its amplitudes. So to delve into that, we need a more advanced theoretical framework, and this is the purpose of this slide, which is a bit technical, but I hope I will be pedagogical. So here we start with the hydrodynamic equations of the two-component superfluid, specifically focusing on superfluid solutions, which are by definition stationary and asymptotically flat. And the goal here is to find the condition of existence of these superfluid solutions in terms of the incoming flow velocity V0, but also in terms of the amplitudes of the obstacle potential, capital U and small u. So you have two momentum equations, here and here, which basically express the energy balance within the two-component superfluids, and two continuity equations. And all these equations are coupled. So what we can do with this, in a first approximation, we use what we call the hydraulic approximation, which allows to neglect all the dispersive terms in the momentum equation. And it is valid for an obstacle which is very wide in the transverse x and y directions. So within this approximation, we simplify a bit the problem, because in this case, the total density and the relative density are algebraically related to the total and relative velocities, capital V and small v. Okay, so we did something with the momentum equations. And now the crucial information comes from the mass equations. So we find that superfluid solutions are supported, provided these continuity equations are elliptic. Indeed, ellipticity ensures that the solutions remain smooth and approach a uniform flow far away from the defect, which is a hallmark of a superfluid behavior. So you can express this ellipticity condition in terms of the local variables within the fluid, rho, sigma, capital V, small v. You have a complicated inequality. But for, or let's say under conditions for the obstacle potential, this complicated ellipticity condition boils down to this very simple local version of the Landau criterion seen earlier. Here, capital V is the local flow velocity, and CD and CS are the local version of the density and speeds of sound seen earlier. Yes?
I don't know what means ellipticity of this equation.
Well, elliptic equations basically describe stationary and smooth flows. This is, for example, the case of the Poisson's equation, Laplace equations. But you have also hyperbolic or parabolic differential equations, which describes non-stationary patterns. So here we fix, we say, okay, the flow must be superfluid, provided these differential equations are elliptic. This is our condition for superfluidity. Okay, so we have this local Landau criterion under specific conditions for the obstacle potential. But this is not the end of the story, because actually we want to have a condition on V0. So we want to transpose this ellipticity condition to V0. So we must know the local velocity field of V. So in a further simplification, we neglect the compressibility of the velocity fields in the continuity equations, which boil down to this very simple Laplace problem, which we supplement with appropriate boundary conditions at the obstacle edge. So you solve this problem, you have capital V in terms of V0, but also in terms of the amplitudes, capital U and small u of the obstacle potential. So this is cool. We have V. And now, once you have V, you can express CD and CS, which are function of rho in terms of this velocity field, capital V, you know. And at the end of the day, so you have a complicated inequality which involves V naught, capital U and small u, which can be reformulated in this way. So the message here is, for the flow to be superfluid, V naught must be smaller than the minimum of two critical speeds, Vd and Vs, which now depends on capital U and small u. So this is plotted here. You have Vd and Vs in blue and orange, respectively, as a function of capital U in the simplest situation where small u is 0, so in the case of a non-polarized obstacle. At low capital U, the critical speed for superfluid motion, which is the minimum of Vd and Vs, has the tendency to decrease, which is physically expected. The higher the obstacle, the more superfluidity is disadvantaged. And at higher capital U, the critical speed has a tendency to saturate to a constant value, which is actually expected for two-dimensional superfluidity in this hydraulic approximation. Okay, so this is what we did. And presently we are exploring the nonlinear mechanisms responsible for the breakdown of superfluidity right above these critical speeds. So this is in progress, but we have the intuition that the nonlinear excitations ejected in the wake of the obstacle are vortex dipoles, also Jones-Roberts solitons, and these nonlinear excitations can be of density type, spin type, but also mixed density spin type due to the fact that the problem here is highly nonlinear. Okay, so this is the superfluid part of my talk. Now let's shift to the experiment done in the group of Thomas Bourdelle at LCF in Paris. So here a condensate of potassium atom is prepared in two hyperfine states, psi plus and psi minus, which are Rabi coupled with frequency omega and detuning delta. Okay. If you assume no velocity in the states psi plus and psi minus, you can express the energy density of the problem in this way, in terms of the total density rho and the relative density sigma. So you have here the Rabi coupling, okay, itself. Here, this is the detuning to the transition, and the last two terms describes interactions between atoms within the same state or between atoms in the two different states, psi plus and psi minus. Okay. And now you focus on the ground state of this problem at fixed total density rho, and you assume that the Rabi frequency is sufficiently large. In this case, you can expand the ground state energy density in powers of rho in the following way. So the first term corresponds to the single particle energy of this ground state. It does not contribute to the dynamics, of course. The second term introduces G2, which is an effective two-body Copley constants for atoms within this ground state. And very interestingly, we have a third term, which is an attractive three-body term with negative Copley constant G3, which is as G2 determined as a function of delta and omega, the Rabi parameters. So a remarkable consequence of this energy density is that the two-component system can now be effectively described in terms of a single scalar field phi with density rho, which satisfies the following cubic quintic nonlinear Schrödinger equation. So you have a cubic term here proportional to G2, which describes effective two-body interactions, and a quintic term here proportional to G3, which describes effective three-body interactions. So an interesting avenue we are investigating for this cubic quintic problem is the formation of dispersive shock waves. So to do so, we consider one-dimensional configuration, which can be realized by tightly confining the gas along one direction, for example, the x-axis. So we have this one-dimensional cubic quintic NLS equation with renormalized coupling constants alpha and beta. And on top of that, we assume the following initial conditions for rho, the density of the field phi, and its velocity v. So we have a step-like initial profile for the density and the velocity. And we let evolve the system according to this cubic quintic NLS, and this is the result we get in the case of zero quintic nonlinearity, so the kind often studied in superfluid. So for the cubic NLS equation. So basically you have the formation of two dispersive shock waves which propagate outwards from the initial sharp step. But in the experiment of Thomas Bourdelle in Paris-Saclay, we have an attractive quintic nonlinearity, and in the presence of this nonlinearity, we predict an interesting deviation from the standard picture. Instead of having two dispersive shock waves, we predict the formation of a contact dispersive shock wave, which is a trigonometric shock which is glued to a rarefaction wave propagating towards the left initial plateau. So in this context, this is a novel nonlinear structure which could serve as, let's say, an experimental signature of the non-integrability of the dynamics due to this quintic nonlinearity. So we are doing numerics, but also analytics within rhythm modulation theory, and playing a bit with the numbers, it seems feasible in the experiment by Thomas. So this is quite interesting, quite exciting. Okay, so let's conclude quickly. Yeah, okay. So we have studied, or we are exploring some collective phenomena in two-component superfluids of light and matter. So regarding the superfluid project, a question remains about the understanding of the nonlinear excitations responsible for the breakdown of superfluidity in this two-component system, but this is in progress. And it would be also valuable to describe the superflow beyond the hydraulic regime in this two-component system, but also for one component. And regarding the cubic quintic NLS study, so we have studied the formation of contact dispersive shock waves in such a dynamics, but future work could also explore other nonlinear structures typical of this quintic nonlinearities, such as anti-dark and king solitons. And looking ahead, we have other projects in mind about quantum correlations in superfluids of light with the group of Quentin, and some non-equilibrium quench dynamics physics in two-component BCs. So that's it, and thank you for your attention.